Rich is a professor in the Department of Psychiatry and Human Behavior and in the Department of Neurology at Brown. He is an epidemiologist with a substantive research interest in cognitive aging, dementia, aging, mental health. He conducts research in delirium, dementia, cognitive aging, and I know he's like become one of the go-to guys for brain reserve and for measurement theory, and for I've like many times asked him for papers as I'm thinking about measurement. His main research is directed at the application of psychometric and latent variable models such as item response theory and structural equation models in cognitive reserve, cognitive aging, and dementia. He's also director of the Quantitative Science Core at Brown, serving psychiatry and human behavior, neurology, in the VA Center of Excellence for Neurorestoration and Neurotechnology, and Senior Associate Editor for Alzheimer's and Dementia Diagnosis and Disease Monitoring and others. And again, we're very honored and lucky to have one of the world's experts on measurement and cognitive reserve here to speak with us. Thanks, Rich.
Thank you, Donna. I will talk to you nothing about measurement and cognitive reserve. Instead, I'm going to talk about methodological and statistical issues and research proposals. We're going to do this talk in two parts. In part one, I'm going to talk about pilot studies and feasibility studies. And in part two, Tom's going to talk about methodological issues and proposals, focusing on some of the proposals that were submitted. So anybody who wants a copy of today's slides, you can scratch down the URL, or if you follow the tweeter, I tweeted it out this morning and put the little @NIDUS. And they're also on the box. Will be on the box. And so not that the slides are that great, but there's some references in there. You can get them and not have to copy them down. So I'm going to talk specifically about pilot and feasibility studies for randomized clinical trials. And I was thinking about why do we call them pilot studies, right? Why do we call them pilot studies? And I'm still not really sure why. The word pilot comes from, refers to people on boats that are usually smaller than larger ships, that help larger ships find their ways through a harbor. And this is a picture from the 20th century, but this is an old word. And so maybe pilot studies are small studies that are meant to guide a larger study through the treacherous waters of a harbor. But there are other uses of the word pilot too, like a pilot light, right? It's a small light that ignites something that's bigger, a bigger study. So maybe that's why we use it. Or maybe, anybody know The Cage from Star Trek? Any Trekkers? So this was like the pilot Star Trek episode. So maybe it's like something to go out and test to see how people like some new product. Or there's Tom Cruise. So I don't really know, and I spent too much time on Google trying to find out why we call pilot studies pilot studies. It's not that easy to find out. So let's just get right into it then and not worry about where words come from, because my hour talk is now 40 minutes, right? So I can talk more about Tom Cruise, or we can get into pilot studies. So this is about designing pilot studies for an RCT, as if you were going to write this for a K or an R03, maybe an R21, or for foundation funding. It's not really about doing pilots that you might do in the context of developing a larger study like a major research grant, where you want to pilot. If you don't already have them published, you want to give your reviewers evidence that you can do the research you're proposing to do. This is relevant for that, but this is really targeted at people who are writing a research grant application, and it's going to be a pilot application. So as you're planning out your pilot, the strategy is to not start by thinking about the pilot, but thinking about the study you want to do that's going to establish you in your career, the definitive R01 you want to do. And then think about all the questions that you have for designing that definitive study. And answering those questions are the things you want to do with your pilot study. So a pilot study is a small-scale study or experiment intended to inform the design of a larger definitive study. Typically focuses on specific aspects of the research related to the methodology, choice of measurements, suitability of the environment, participant availability, and resource allocations. It's important to remember what a pilot study is not. A pilot study is not a little version of a definitive study. It's not what you call a study that you design that looks just like the definitive R01, but you just don't recruit as many people because the pilot study budget is smaller. It's not intended to develop a target effect size through an efficacy analysis, although there are ways we can use pilot studies to help inform what the effect size should be in the larger study. And it's not a label applied post hoc to a study that you did that didn't achieve statistical significance, okay? You all know that, right? I know you know that, but people do it anyways. So what's the purpose of a pilot study? It's to provide preliminary information about the feasibility of doing a definitive study or trial. Are the participants you'd like to recruit really available? Like, I want to do a study and I want to apply this intervention to people who have some cognitive impairment, but they're not demented, they have some mobility limitations, but they're not completely bedridden. And so you think about identifying these people who end up being unicorns and you can't find them in the real samples, right? So who's going to be in your definitive R01? Go out and see if you can actually find those people in your target sample. How many people are you going to have to screen to enroll the people you want to enroll in your definitive study? Can the measurements you want to do be done on these people? Like, you know, a person in 2 casts came up earlier today, right? You have a lot of written exams you're doing for your cognitive tests. Is that going to be a problem for people in a hospital bed? Is the environment suitable? Is the resourcing adequate in particular time? You can do a lot to get preliminary information about the outcome measurement variability, including the degree of natural variation in your outcome endpoints, and perhaps identifying predictor variables or stratifying variables that are important to consider in the design. You can get information about your outcomes, performance characteristics, and do things like establish the reliability of those measurements in people you would like to use to collect those outcome instruments. And you can get information about the sample selection. Are there particular subpopulations who are ill-suited to enrollment in your study? Should certain populations be overrepresented or excluded? And is there evidence for effectiveness or efficacy or safety that may vary across populations? Wait, did I just say effectiveness or efficacy? Yes. So is the purpose of a pilot study to look for suggestive evidence of the efficacy or effectiveness of your treatment? Well, you got to be careful here. That's why the caution sign is up, right? Let's go back to the pilot, right? Which boat do you want to use to bring your goods to market? The container ship? Yes. Here's your prize. I don't have a prize. Good. Very good.
You can't follow that.
I'll just look for something. What can I give? Here's a pitcher of water. Okay, there's a lot of text here, so I'll slow down. But you don't need to read the text. All on me. It's wrong to look at efficacy in your pilot study, okay? It's wrong because you're underpowered to do so. You're just as likely to find evidence of harm for a treatment that's really effective if in a small underpowered study as you are to find evidence that it is effective. And so you really shouldn't look at it at all. And you may even find an inflated estimate of efficacy, which can be just as bad as finding evidence that it does harm, because if you use that inflated estimate of efficacy to power your definitive trial, you're going to end up being underpowered. So it's just very dangerous to do this. But why do I say you're going to have to look at it anyways and include that in your definitive study application? Well, it's because, I'm going to skip ahead. I'm going to get to these, don't worry, I love these. Why? One, your reviewers and your mentors may not know that it's wrong to do this, right? They're just people. Not everybody knows this and gets it, right? And if you don't include your efficacy analysis, they're going to be like, what? Why didn't you show me? What did it look like? You're hiding something? No. So you have to do the analysis. You have to hope and pray the confidence interval is consistent with what you would like to target or envision as your effect size, and we'll talk about what that means. And then you have to educate the reviewers. You have to say, look, here's our efficacy estimate, but this doesn't really mean anything. Why? We have low power. Our result could be anywhere. Here's the confidence interval. And also hope and pray that it's at least suggestive that there's a positive effect. Now, if you're doing your pilot study, you do your efficacy, and you have an effect that indicates harm, does that mean you can't proceed with your full trial? No, of course not, right? Now I'll tell you. Here, I'm going to show you a picture. This is a picture. It's a distribution of effect size estimates from 10,001 studies. It's made up data that had a true population effect size of 0.5 standard deviations, which is about as good as you could ever possibly expect in health-related research. And there's 25 participants per group. So it's a t-test, 25 participants in a treated, 25 participants in an untreated group. Do the t-test, calculate the Cohen's d. The Cohen's d in the population is 0.5. What do you get in your pilot study? Well, the distribution shows you could get a result all the way from negative 0.5 to over positive 1.5 if you repeated this study 10,001 times. Where's the one that you did? Pick your point, right? Well, you got a good chance of getting it towards the middle, but it could be anywhere. And the power of this design is 41%. So with 25 people per group, you've got a 41%, which means that for 41% of these dots, the lower bound of the confidence interval is exceeding 0, right? So you've got low power, confidence intervals are wide, and in the population, the treatment effect is very strong, but you could end up with a sample, with a result from your pilot studies that indicates harm. So the question was, my pilot study suggests harm. Can I go on with my R01? And the answer is, of course not. But now you're going to have to work extra hard to convince reviewers that even though the pilot suggests harm, the true value could be beneficial. So give them a graph like that. Why not? Here's a distribution that might look very similar, but the center is at 0. Here's where the population value for the treatment effect is at 0. When you put these two together, you can see that even if you did your pilot study and your effect size was about 0.5, there's a pretty good chance that it came from a population of hypothetical studies, the red studies, where the population value was 0. And this mixed up plot is for when there's half of the now 20,002 studies you've done were from an intervention that is truly ineffective. It has a treatment effect of 0. Those are the red dots. And another half of these studies come from a distribution of hypothetical studies where the true effect is positive 0.5, a medium effect size, which would be pretty good for a health-related outcome. And in the bulk of where you're likely to get most of your effect size estimates, where the greatest density is in this plot, you've got like a 50-50 chance of picking an intervention that comes from one that was from a truly null distribution or a truly efficacious distribution. And this is when there's a 50-50 chance that the intervention is truly effective, right? But nature, she's tricky, right? And we're just figuring her out. What if the prior probability of having an efficacious treatment was only 20%, right? So now you're looking at, well, I don't really know anymore. But maybe you're really smart. I'm looking for Wes. Where's Wes? Maybe you're picking interventions that really work. And now you got a good chance with a positive 0.5, but you really don't have any idea what the prior probability of have picked a good treatment that comes from an effective distribution. Anyway, here's what it would look like if you powered your study to have 90% power. So you can see we still have, it's the same distribution of null treatment effects, but it's shrunken up towards the middle because now instead of 25 people, we've got 86 people in each group, and there's a much greater peak for possible effect sizes under the assumption that the treatment really does work. And so that's why we want to have adequately powered studies. But I'm not saying to get 86 per group for your pilot study, because that would be a study powered for 90%, and that wouldn't be a pilot anymore. That would be a definitive study. Okay, so I did this one. All right, so here's the question you all want to know. So if I can't use a pilot to identify a target effect size, how do I come up with a target effect size? Does anybody have that question? You better, because that's the other half of the show. Okay, so the idea has been around for a long time that you have to come up with, ahead of your study, some definition of what the critical effect size is for your treatment. And Wes gave an example yesterday where he just decided that the effect size that he wanted to detect was a 10% reduction in delirium risk. And that's a really great way to define what a critical effect size needs to be. It's you rely on expert judgment, and you talk to smart people in the field, and they tell you, well, if you don't come up with 10% reduction, no one's going to care. That's great. That's your effect size for your power calculation for your definitive R01. But there are other ways to do this, and some people call these concepts words like minimally clinically important difference or minimal clinically important change. Sometimes we drop off the clinically, and so it's just minimal important difference or minimal importance change. And there are analogous terms used in other fields. So the MCID or the MID is a term that's become popular in health services research and driven a lot by researchers in rheumatology. But in psychology, there's a related concept that's known as reliable change. And in epidemiology and public health, we talk about things like number needed to treat. And Doug told us about cost of benefit, cost effectiveness, and cost utility values as well. So what are these things asking? What are these things defining? So the MCID is telling us how much difference we have to observe to conclude that the difference is equal to or greater than some threshold determined to be clinically or practically significant. So you can come up with MCIDs using an expert method. Where we asked Wes, what should we get? There are research designs you can use that involve interviews with patients and clinicians, and you ask the patient, so you've changed from this state to that state. Do you feel any better? And you collect a lot of ratings of how patients rate their sense of improvement, and you can relate those values back to values you observe on changes on your outcome measures, and that becomes a way of defining what is a typical change on the outcome measure that's related to change and patient rating of real change on the outcome. And that's a perfectly good way of doing your MCID definition. There are other ways to define MCID that involve just looking at what the standard deviation is on an outcome measure. And that gets us closer to what the psychologists have defined as the reliable change index. So the reliable change index is asking a slightly different question. It's how much difference must we observe in order to conclude that the observed difference is greater than what we would expect it due to measurement error and other measurement artifacts like practice and retest effects that came up earlier. And so there's a little bit of overlap between the MCID when it's defined using distributional approaches and the reliable change index as used in psychology. And one issue with both of these methods is, well, the MCID, if you're doing an anchor-based approach, which involves using an external measure to define what is an important change for a patient, I'm wondering, why don't we just use that anchor-based method as the outcome in my study? Why am I using this other measure? Because then why don't I just ask patients if they feel better and let that be the outcome? If it's a distribution-based approach, we have this issue of using between persons data to make assumptions about within persons change. And sometimes, as you know, public health interventions can have small effect sizes when you look at as the group effect, but it can make a really big difference for the people who are benefiting, and it can make a really big public health impact if the health condition is expensive. So now let's look at what public health and epidemiology gives us. So one is like the prevented fraction, which is like the inverse of the attributable risk. How much of the disease can I prevent by doing the treatment? And we can actually use some cost benefit or cost effectiveness tools to try to come up with what's the smallest effect size I need given how much my treatment costs to fall under the cost benefit ceiling ratio that Doug told us about yesterday. And I actually found a reference that did it. I asked Doug yesterday, and so now you can get the reference. So you want to read more about these methods. Here are 3 references. The first one from Engel is from 2018. I wanted to get a really current reference for that because the language and the techniques change a lot in that field for MCID definition. I found a really cool reference for reliable change in schizophrenia. This was published in 2016. And this one uses both reliable change and the minimal clinically important difference to identify outcome metrics for a clinical trial. And then if you want to do numbers needed to treat, any epi textbook would work. And if you want to use cost benefit or cost effectiveness analyses to set a target for clinical efficacy, I did find a reference in the British Medical Journal. Okay, when all else fails, you should all know about this nice paper from Jeff Norman that was published in 2003. And I often have to fall back to this paper in helping people design research studies. And he has a very nice paper where he makes arguments, and some of it's supported with simulation and empirical research, that in most cases, a half standard deviation effect size is a good target for health-related outcomes because that's about the difference that people can appreciate. It's related to that just noticeable difference concept from, we had a psychophysicist. Someone who was doing psychophysics earlier? Joe? Okay. So, what would a pilot RCT look like? Here, I'm going to give you the aims for your pilot, RCT. You can copy these down and put these on your specific aims page. You might change some of the words. Aim 1, treatment development activities. So this is where you're developing your intervention manual and your protocols for delivering the treatment program, manualizing the treatment. And there's no aims or hypotheses associated with that. It's a work product. Aim 2 are feasibility to assess acceptability and design issues. Things like, are the patients really available? And can I train my interviewers to deliver these measures? And how many people am I going to have to screen in order to get the sample size that I want? And that has sample size implications. And then aim 3 will be to estimate some key statistics that you'll need to calibrate your sample size for the major study, including what's the standard deviation or an estimate of the standard deviation for the outcome variable? What's the reliability of the outcome variables, and or what's the correlation between your outcome variable at baseline and follow-up? That can be really helpful to help. Knowing that can help drive down your power for pre-post studies where there's a change in an outcome measure. And what's the expected distribution of the outcome measure in the absence of treatment or in a normative sample? And that can be really good if you want to use that 0.5 effect size change criterion. So here's more feasibility and acceptability issues for aim 2. So the questions may be things like, how many people can be approached? What's the size of the patient pool? So then you have to go and look at admission records and see how many people are actually coming in. How many are likely to be eligible? It's the second question. What proportion of those eligible would be willing to participate in research? Now you've got to go out and interview people. Hey, I'm going to do a research study. It's going to involve taking fluid out of your spine. Would you be willing to participate in this research study, yes or no? Well, you really want to know that, right? Before you start your big study. I'm going to take blood out of your jugular vein. Would you be willing to participate in this research study? You might want to know. Are people willing to participate in that kind of research? And then what proportion of those people randomized to treatment will actually comply with treatment? Oh, you mean this spine? Oh. Okay, no. You want to know that too. And what proportion of the people who enroll will complete follow-up, right? They'll be running away from you, right? So you can't catch me. Okay, so then you want to know, well, how large does my pilot have to be? So the right answer is you have to be clear about your questions. The answer is going to be framed in terms of how precise do you want to know these things rather than hypothesis testing. And the third point is consider work with an expert statistician or methodologist to get an answer because it's nuanced. And it's actually much harder to do a power calculation for these, for things that aren't strict hypothesis testing situations. And so I wouldn't recommend embarking upon it on your own. Get some professional help. While you're waiting for the statistician's answer, plan on 25 per treatment arm for budgeting your pilot. I think 25 is probably a good number, but you want to have a serious number. Here are some screenshots from my phone, not really, of a conversation I had with an investigator. They said, how large of a sample do I need to estimate percent within plus or minus 5%? So I say, well, what proportion do you expect the proportion to be? Say 75%. So then I say, how confident do you want to be in obtaining a margin of error of plus or minus 5%? To which they say, question mark, question mark, question mark, confused face emoji. So after a pause, I say, sometimes people say 95% when I ask them that. Okay, 95%. But I think people really mean 80%. Okay, 80%. Or even one-sided 80%, which is two-sided 60%. To which I get question mark, question mark. Oh, no question marks. Just angry, confused emoji. It's okay, I got an answer for that. One-sided 80% means 80% confidence that the proportion is at least 70%, 75 minus 5. Oh, okay. 80% one-sided. For that, you need a denominator of 54 people. And then they're thinking to themselves, I know what they're thinking because I wrote it, but I know they're thinking, well, 80%, that's kind of low, right? I'm worried that's not going to be high enough. So what about 95% two-sided? Well, that you need 289 people as the denominator for that proportion. Okay. Right? Maybe 80% one-sided is okay. It is a pilot study. But we got to be careful there, though, because just like getting an effect size estimate that's too high can be dangerous, getting a bad estimate of what the proportion is who are going to be eligible or are going to be willing to have a needle stuck in their spine or jugular vein can be very damaging for your full study. So you do want to make your pilots as large as they can be to get as accurate estimates as you need for these parameters without busting the bank and without doing a definitive study. So then this conversation went on, by the way. Do you have a calculation for this? Do you have a citation for this calculation? To which I said, it's pretty basic. It's just the equation for a confidence interval on a proportion. And I nicely provided it for anybody who wants it. Rearrange to solve for the smallest n where the margin of error is less than 5.05. To which they say, please? And this goes on. I also checked my calculation with a Monte Carlo simulation. 54 is right. Remember the question, right? Wonderful. Have a nice trip to Monaco. Can I please have a citation for your calculation? So I finally gave it to him. And look, smiley face emoji. Everybody's happy. Okay, so let's end up with your assigned reading before you embark upon your design of your pilot study. Everybody should know about Leon, Davis, and Kramer, 2011, which is the role and interpretation of pilot studies in clinical research. This is a really nice paper written for applied researchers and probably says everything I said up here already. I probably plagiarized without knowing it. That's because I learned it, right? I learned it. A more technical paper is one by Kramer and others, published in 2006, Caution regarding the use of pilot studies to guide power calculations and study proposals. That's the one that says, don't use pilot studies to power your full study. And don't make a decision as to whether or not you should proceed with intervention on the basis of a pilot study. And because both of those papers and the real motivator or the real driver behind those papers is Helena Kramer, this information is widely known in psychiatry. It's less widely known outside of psychiatry. And that's why, as you're writing your pilot study, you have to know this stuff because you're going to have to teach your mentor and you're going to have to teach your reviewers this information in order for them to evaluate your proposal. And remember what Lucy said, right? She said, tell your reviewers what they need to know to favorably review your proposal. Tell them why what you're doing is an important and relevant pilot study. Don't just give them a pilot study and expect them to know, oh, this is great. They're doing all these things that are important. You have to tell them, we're doing these things and they're important because blah, blah, blah. Okay, what else is here? So those are bolded for a reason. They're really important. What else do I want to point out? The Orsmond paper, 2015, I just learned about this week. It's from an occupational health journal, but it's got really nice lists of questions you can ask in a pilot or feasibility studies. So, I'm going to stop and ask for questions. And I got us back on time, I would just like to say.